A gate at a busy terminal. Passengers filing through the jetway, overhead bins slamming, a flight attendant counting rows. Standard morning departure, but sitting against the wall near the gate desk, a full skydiving rig. Harness, deployment handle, reserve chute. Most people walk past and assume the answer before the question is asked. Parachutes on planes. Too expensive, too heavy, too impractical. Obvious. None of those are the real answer. The real answer has 5 layers, and each one makes the previous look shallow. Engineers didn't skip parachutes out of laziness or cost cutting. They ran the physics, ran the numbers, and concluded that parachutes solve a problem that simply doesn't exist in the scenario where passengers think they need one. The first problem isn't the parachute, it's the sky. At 35,000 feet, the outside air temperature sits around -70 degrees Fahrenheit, cold enough to incapacitate exposed skin in minutes. But temperature isn't even the primary problem. The atmosphere at that altitude is so thin, so depleted of usable oxygen, that an untrained person loses consciousness within 15 seconds of exposure. Not minutes, seconds. The body doesn't fight it. It simply shuts down. So before a passenger could reach for a ripcord, before the canopy could inflate, before any of the mechanics of skydiving could begin, that person would already be unconscious. The parachute doesn't become irrelevant after the crisis. It becomes irrelevant before the crisis even registers. The sky kills the premise before the equipment gets a chance. But there's a problem that comes before the altitude problem, something that stops the whole scenario before it starts. Nobody is getting out of that aircraft. A 737 cruising at 550 miles per hour generates more than 4,000 pounds of aerodynamic pressure against the cabin doors. Not a lock, not a warning light. Raw physical force, the rough equivalent of stacking 2 adult horses against the door and expecting someone to push through it from the inside. A human being cannot do it. 2 humans cannot. No mechanism a passenger can reach would move that door while the aircraft is at cruise speed. This is the part that rewrites the mental picture most people carry. The imagined scenario is opening a door and jumping. That opening is not a design challenge. It is a physics impossibility. Trained pilots have no procedure for mid-flight passenger door exit, not because it was never discussed, but because it is not achievable. The procedure doesn't exist because the situation cannot exist. Now grant the hypothetical. The door somehow opens. The air is somehow breathable. A passenger can step into open sky at altitude. They would still most likely die, not from the fall, but from the parachute itself. Skydiving looks like pulling a handle and floating down. It is not. Every trained jumper spends months on body position before attempting a solo jump. How to orient during free fall, when to deploy, how to manage opening shock, how to steer the canopy, how to land without catastrophic injury. That training happens at 3,000 feet in controlled conditions with an instructor nearby and a radio in the helmet. At 35,000 feet, in a crisis, with no training, the chute becomes the danger. A mistimed deployment at the wrong altitude tears equipment. Opening shock at high speed causes serious injury before the canopy fully inflates. A passenger who has never practiced a landing will hit the ground at a speed and angle that survival statistics do not favor. Untrained parachute deployments are routinely fatal even at low altitude in good conditions. The tool requires a person who knows how to use it. Without that, the equipment is not a rescue device. It is a different way to die. Here is the layer most people never reach, and it changes everything. 80% of all commercial aircraft accidents occur during takeoff and landing, not at cruise altitude, not at 35,000 feet. On the runway, in the approach corridor, in the first 2 and last 8 minutes of flight. Those phases account for the overwhelming majority of aviation's fatal history. At those moments, a parachute is completely useless. At 500 feet on final approach, there is no altitude for deployment. There is no time to recognize the emergency, unbuckle, move to a door that still cannot open, and exit. Even if every other obstacle vanished, the altitude isn't there. A parachute requires several hundred feet of clear freefall just to inflate reliably. At the very moments when commercial aviation is most dangerous, the geometry of the situation makes the equipment irrelevant before a hand ever touches it. The scenario most people imagine, catastrophic failure at cruise altitude, time to act, a controlled exit into open sky, almost never describes an actual commercial aviation emergency. The crash the public pictures is not the crash the accident record describes. The tool designed for the imagined emergency doesn't function in the real emergency. Even after all of that, assume every problem is solved. The door opens. The air is survivable. Every passenger has the training of a professional jumper. The altitude is right. 189 parachutes weigh between 1,000 and 1,500 pounds. That weight doesn't sit in storage and wait for an emergency. It flies. Every departure, every landing, every route, every day for the entire operational life of that aircraft. Airlines strip weight obsessively. Seat designs get lighter with each generation. Meal carts are weighed before loading. Magazine racks were removed from some fleets because the paper added up. That is not cheapness. It is a continuous fuel equation calculated across tens of millions of flight hours. Every extra pound costs real money on every flight, compounding over years. 1,500 pounds of parachutes burning fuel perpetually to address a scenario they demonstrably cannot help with in most emergencies. The arithmetic does not support it. What that weight budget buys instead: redundant hydraulic systems, fly-by-wire controls with multiple independent backup pathways, structural margins that allow airframes to absorb enormous stress before failing, better crew training at every level. The engineers did not ignore the parachute question. They calculated it. The better return was preventing the accident, not escaping one the parachutes couldn't reach. In 1971, a man calling himself D.B. Cooper hijacked a commercial flight, extorted $200,000, and jumped from the rear staircase of a Boeing 727 somewhere over the Pacific Northwest. He was a trained jumper. He chose his conditions deliberately: low airspeed, low altitude, a specific aircraft with a rear door that could be opened in flight. He brought his own equipment. He planned every detail of the exit in advance. He was never found. That jump is the closest thing aviation history has to a successful mid-flight parachute exit from a commercial aircraft. It required skydiving expertise, meticulous planning, a cooperative crew, and an aircraft type that no longer exists in commercial fleets. It is not a template. It is a controlled outlier that proves the rule, and nobody even knows if he survived the landing. Now look at that skydiving rig at the gate again. The harness is fitted for one person who was trained to wear it. The deployment system assumes a practiced hand under a clear protocol. The reserve chute assumes someone who knows when the primary has failed and exactly what to do in the next 3 seconds. Look at the cabin instead. That exit row placard is not a launch instruction. It is a ground evacuation diagram for when the aircraft has stopped, is on fire, and 200 people need to move through a narrow opening in under 90 seconds. The oxygen mask that drops from the overhead panel is not for an exit into open air. It is for keeping passengers conscious at altitude while pilots execute an emergency descent to breathable levels. The brace position, the one flight attendants demonstrate and passengers largely ignore, is statistically shown to reduce spinal loading and preserve consciousness through impact. None of these are theatrical gestures. All of them are calibrated for the accidents that actually happen, not the one most people imagine. There is one genuine exception worth naming. Some small ultralight aircraft carry whole aircraft parachute systems, a single large canopy that lowers the entire plane. Cirrus aircraft are equipped with this, and it works. But those planes weigh a few thousand pounds, fly slowly, and operate at altitudes where the math allows the solution. A loaded commercial jet weighs upward of 150,000 pounds at takeoff. The canopy required to slow it to a survivable descent rate would need to be the size of a city block. The physics scale completely differently. The exception explains exactly why the rule exists. The question most people ask is why planes don't have parachutes. The better question is which scenario would actually require one, and when that gets answered honestly, the scenario almost never fits how commercial aviation actually fails. The engineers were not negligent, they were precise. The best safety system is the one that makes the escape unnecessary in the first place, and modern commercial aviation has become extraordinarily good at exactly that. But engineers have never stopped asking the harder version. Not how passengers escape a failing aircraft, how the aircraft itself survives what was once considered unsurvivable. Whole aircraft recovery systems, controlled impact airframe geometry, automated emergency descent protocols that activate without pilot input. The next layer of aviation safety is not about giving passengers a way out. It is about designing a machine where the situation requiring one almost never arises. That skydiving rig at the gate was never going to save anyone at 35,000 feet. The engineers understood that before the first commercial jet ever left a runway. What they built instead is the reason that gate scene is completely unremarkable, and the reason most people board a plane, settle into their seat, and never think about any of this at all.